Yeah, you would, but it's a lot of work to get up to the higher and higher, and you don't need it. So you can use this relatively impure stuff, and you get your. And the question is, why not use higher purity? You don't need it because the reactor will work. In fact, Fermi's first reactor, its pile that we had a demo here, he was using natural uranium. They didn't know how to purify it yet, and he was using natural, and it worked. Maybe even with a few percent, you can get a reaction to go, except it won't be a bomb. To make a bomb go, you really have to get all of the stuff to go immediately. In a reactor, it can go slowly, and you want it to go slowly because you don't want the thing to take off on you and melt or blow up. So there, even with less than 1% uranium, you have enough neutrons to trigger off things, and you can get a chain reaction going, self-sustained, but it won't explode, and you don't want it to. In fact, they have these control rods made of cadmium, which absorb the neutrons. So what you do is you start out with the rods near each other. Well, the other trick is that they put it in graphite to slow them down, because it turns out that slower neutrons are more effective. That's something not obvious, but it turns out that slower the better, so it sort of creeps into the uranium nucleus and poof, it doesn't zip through. So you had to know that. And also you don't want too many of them, because then they'll run away. So they have these control rods which they pull out and they see the reaction building up, and when you're just about to go, you keep the rods right there. And that's what Fermi did, in Chicago no less. And he assured them that it wouldn't detonate. it was in the, you know the story, it was in the squash court at the University of Chicago. They built this thing. In Chicago, if the thing had gone off, there would have been a mess. But Fermi said, no, don't you listen to me. I know what I'm talking. In his best Italian accent. So, and he was right. He was a very good, smart guy. Gutsy, though. You know, I mean, I don't know how. I'm sure he didn't ask the mayor. That would have been too much. Anyhow, so we know that if you do get extra neutrons, like in our demo here, we had 2 balls, and my friend here dropped 1, and the balls went all over the place, triggering all these. You get it to go. Okay, then. So that's basically what they do. This is basically the kind of reactors that they have for producing energy. Instead of graphite, they put it in water to slow the neutrons down and to collect the heat. And you can get heat out of this. Boils, it brings heat through here. You boil water, you make steam, you turn a turbine, you use Faraday's law to generate electricity in a generator, you cool the steam down and you recycle it through. And that's how you get a boiling water electric generator plant. Now, the trick is in the atom bomb, this is well-known stuff, so you don't have to have a security clearance. The idea is you have to get the critical mass. So what they do, the simple bomb is the one uranium-235, and that's what apparently the Iranians are trying for, if they're trying for it. What you do, you have 2 pieces of uranium, and neither of them is critical. So they may be reacting a little bit, but slowly. But what you do is you want to bring the 2 pieces together and keep them together long enough for the explosion to go, but before it flies apart, because it is exploding. So they have what's called a rifle type thing, where there's an explosive here, and they just shoot this piece of uranium into this one here, and this makes the mass critical. And this is, then the thing explodes, because naturally the reaction can go and the neutrons can't escape from the critical mass. It turns out, however, that there's another element, plutonium, which is a byproduct of that nuclear reaction, but the plutonium, it seems, will spontaneously start to react, and the rifle thing does not work well enough. So there you have to have a different thing, where you have a plutonium in a shell, and you put explosives around it, and you implode the pieces of plutonium, and that's how you get the critical mass. This is much harder technically to do because you've got to get all those explosions to go off at the same time, and apparently it's a pretty tricky thing to do. So although plutonium is somehow easier to make, and it's also a byproduct of nuclear reactors, the people that want to make a simple bomb go for uranium if they can get it, but it has a problem of purification. In any case, here's a picture of the bomb. The first bomb that they tried was the plutonium bomb. They were pretty sure the uranium bomb would work. So they tested the plutonium bomb. The first test was the plutonium. They called it Fat Man because it had all these explosives around the outside and crushed it. In fact, the bomb they dropped on Hiroshima had never been tested. They were so sure it would work, that rifle type thing, that this was the first time it had ever gone off. Okay, so, but the other thing, I don't want to leave you with a bad feeling about radioactivity. It's bad enough. But, I just want to point out that nuclear medicine is a very big thing. And I point out the work of Rosalind Yalow, who won a Nobel Prize in Medicine and Physiology in 1977, where she tagged things with radioactive elements like insulin. She could put in a radioactive tag, and what she does is, it's an assay. So you're trying to figure out how much of something is present, like insulin, like how much insulin is in the blood of a diabetic person. So she would tag the insulin with a radioactive element, and then she put it in with regular insulin. And the regular insulin would displace the radioactive stuff. Then she spun it down and found out how much of the radioactivity was in the antibody and how much was in the supernatant here. And so she could tell, because of the concentration of the, this is what she's trying to figure out, the assay of this species, how much of it replaced the radioactive stuff. And by measuring the radioactivity, which is very precise, because if this stuff is giving off gamma rays, you put a Geiger counter there, you can measure very precisely how many gamma rays you're getting. And against a very bad background, a weak background. So it's a very precise, and she in her Nobel Prize address, she said, well, gee, I can see picoliters of stuff, and I could, in fact, the amazing thing was she got revenge on one of the first reviewers of her paper, who rejected the paper by saying, you claim that insulin acts as an antigen, namely that the body will have antibody to insulin. But insulin is a small molecule, and up to that point, about 1960, people only thought that you get antibodies to like bacteria, right, a big thing. But her research seemed to show that insulin, a small molecule, was also creating antibodies. And the reviewers rejected that. They said, all the experts say this doesn't happen. And so the only way they got the paper published was by taking out that line. They took it out, and so they got it published, and then they proved later that indeed insulin does create antibodies. And so you could use immune system to do this assay, because it's an immune reaction. You're getting the antibodies to insulin to react with it. So this is a great thing. And funny, just yesterday I came across some lady in New York, what's her name? Darakova in New York. They're using radioactive things as this is not an assay, but this is a therapy, where they think they can attach a radioactive thing to an antibody to like HIV. And this thing will carry a radioactive thing and attach to the HIV and kill it. And she claims that she has reduced the titer of HIV in very sick people by this immune, it's sort of a radioimmunotherapy. It's not an assay, it's a therapy. So you can look that up. She only talked about it a couple days ago. So I think that's really fabulous stuff. I'm sorry. Now, look, I wanted to, so that's enough on radioactivity as far as I'm concerned. And probably as far as you're concerned too, that's enough. But I did want to do one other thing, namely, I just want to mention one quick thing, and namely that where does color come from? Because we talk about all these fancy things, namely energy levels, Bohr levels, Schrodinger equation, all that sort of thing. But it has an impact in our lives. Typically, you can think of an energy level as being like a resonance. Remember, we have the idea of if you have a thing with a spring and you can move it, but if you get near its natural frequency, you get this big motion, which is represented by a curve like this. The motion is modest, but then when you get near the natural frequency, the amplitude got very big. We did something on a spring and it actually jumped off the spring. You remember that? And in fact, it turns around and does something like this. This is the amplitude. And moreover, it absorbs energy at that point. This is unfortunately not coincident, but that's the same frequency where it absorbs energy. Okay, so this is more or less how you could represent what's going on in an atom. But it turns out, I think we said, that the reason the wave slows down in a material is that the atoms in the material are oscillating. They're re-radiating the radiation. If they have a big amplitude, you have a big re-radiation of the amplitude, and you have a big slowing down of the waves. So this kind of curve tells you that if you're near the resonance of an atom, the wave will slow down more, which is called the refractive index. Because remember that we said that refractive index was the velocity of the wave is given by c over n. And that n comes from the fact that you're near a resonance. And if the amplitude is large, you get a big slowing down. And the fact that you're near the resonance, it will depend on the frequency that you're at. So you see, here's might be the blue n, and here might be the red frequency. If you're on this side of the curve, the blue light causes the oscillation to be greater, so you have a larger n for, say, blue light, if you're on this side of the resonance of an atom. And this explains dispersion, because what Newton already and others had discovered was that if you shine light through a prism, you spread out the light red to blue like that, and the blue has a higher bending, which means that it actually has a higher refractive index. So the index of refraction depends on the frequency. In fact, it depends on the frequency from the resonance frequency of the material, of the atoms in the material. So that basically, in a nutshell, is why materials have a slowing down of light and why it depends on frequency. In fact, if you're on this side of the curve, the blue would be refracted less, as a matter of fact. And that's observed too. So it depends on where the resonances of the material are. I think that's about all I dare say about this, but I just didn't want to leave. Oh, and well, the consequence of this is we know that things reflect off a surface if there's a change in speed, right? Because if a thing has uniform speed, there's no reason for it to reflect. It's like uniform, so why scatter? But if there's a change in speed, then a thing will reflect off. Moreover, there's absorptions nearby, like this. So the material will both reflect and absorb the light. So the color comes from the fact that you have a change in index of refraction, and so you'll have a reflection off that surface, which is due to the change in index. Right? Did you get that point? Yeah. So why we see each other is really we're near atomic resonances, and the different colors is because different materials have different resonances. We know that, for example, hydrogen has resonances in one place, helium has red lines someplace else. So that's what's doing that. And so each color that we see is the fact that there's an atomic resonance there, and you're changing the index of refraction differently for different colors, and therefore we see different colors. I think that's really great. I mean, people 100 years ago didn't quite understand this, but we pretty much understand it, and it's all quantum mechanics, basically, deep down, right? So that's very good. I have some more slides here. It builds up. So this is an index of refraction, and reflection, and also. Oh, but this is an interesting point. Sorry about this. But there are all kinds of resonances and stuff in your material. For example, what I was talking about there is atomic resonances, and they are more or less in the visible range. But you also have other vibrations and resonances in material. For example, the molecular vibrations. So actually, you'll get, if you look in this frequency range, which is invisible, but if you had the instruments to do it, you would see strong reflection in the infrared due to the molecular vibrations, or a low frequency, because again, it's very sensible. The high frequency things are electrons moving because they're light and they have a certain force, and so they move very fast, so they have a high frequency. The molecular vibrations are atoms moving, so they're more cumbersome. They're the linebackers, they're kind of slower than the running backs, and they're slower. And so you'll have vibrations around here in the infrared. And then we have the other possibility is dipoles, like with water. You could have dipoles going here, but that's the whole molecule turning, so their frequency is much lower. So we have all kinds of spectra, and it reveals what's going on in the material. For example, if you have dipoles, you'll get something over here, and if you have molecular vibrations, you'll get things in the infrared vibrating reflections, and then you have your electronic motion. Now, I think I can't resist but show you this. For liquid water, the index of refraction is very high. Like, I don't know if you remember, glass is like 1.5. Water, the index of refraction is 9 in a low frequency range, because what do you have there? You have giant molecular dipoles, and they, when you jiggle them, they emit very strongly. They slow the waves down. What did I change here? The index of refraction here is 9, but those molecules can't follow very high frequency. As the frequency goes up, those molecules stop. They can't follow anymore. Then you have a bunch of atomic molecular vibrations here, and then you have electronic here. The fascinating thing about water is that where this is the index of slowing down of light. This is the absorption by water. It's enormous, except right in the visible range. It's in between the molecular vibrations and the electronic. So water is transparent in the visible, but it's opaque in the infrared and over here in the X-ray region. That's the reason you can see, when you go scuba diving, you can see like 100 feet into water. If our light, visible light, were shifted over here, it would be like black. You would see like a fraction of a millimeter only. The light would not penetrate. This is the absorption. It's really an amazing thing. It changes by about 7 or 8 orders of magnitude, like 100 million fold in going from this frequency to here. So if you try to send light of this frequency, infrared through water, it doesn't go at all. It's absorbed immediately. But here in the visible, it is. And I point this out, this like miraculous thing. I can't resist telling you this. How the coincidence of all the light that we deal with. For example, the sun sends out a black body radiation according to its 5,000 degree temperature in this range, which we call the visible, which we can see. Okay. Then the amazing thing. So our eyes are adjusted to that. But the other thing that's an amazing coincidence, or whatever, is that light passes through our atmosphere almost perfectly. In the visible range, the transmission is excellent, like 95%. If the light were over here, let's say the sun were cooler, and it was emitting over here, the light would not reach the Earth, nor would it penetrate water. So everything would be black. It's a really amazing coincidence that the sun and the atmosphere and water all transmit in just this range. It's just a marvelous thing. At this, in the visible light, the sun emits there, the eyes are sensitive there, and the Earth's atmosphere transmits there, and hardly anywhere else, and water transmits there, just there. I think otherwise we wouldn't have life. Okay, so it's 4 o'clock. Well, thank you. It's been a great course. I appreciate you being here. Oh, by the way, let me add, you got a schedule of review by the GSIs. I'll put down my schedule again, and I'll send you an email. But I will be here, Monday, 3 to 4 in LeConte. Wednesday, 2 to 3, office hour. And Friday, 2 to 3, office hour, and 3 to 4 in 1 LeConte. I'll also send out a list of topics that we will not be covering on the exam. There are some of those, not a lot, but some. And you want to know about that. And I'll send out a sample final exam, okay? Study well. Take care.